Deep in the vast stretches of space, where the laws of physics twist into the unimaginable, there exists something far stranger than a black hole. Picture a cosmic fountain, endlessly pouring out matter and energy instead of swallowing them whole. What you're seeing in your mind isn't science fiction, it's a white hole, the bizarre twin of a black hole that defies everything we know about reality. While black holes pull everything in, never letting go, white holes do the exact opposite. They push everything out, refusing to let anything in. Today, we're diving into 25 of the most mind-bending discoveries about these cosmic enigmas. From their role in Einstein's equations to the wild theories that suggest they might be gateways to other universes, each revelation will challenge what you thought you knew about space and time. If you're ready to have your understanding of the universe turned inside out, keep watching, because white holes might just be the strangest things lurking in the cosmos. Now let's peel back the first layer of this cosmic mystery. One of the most captivating ideas about white holes comes straight from the heart of theoretical physics, the notion that they could be black holes running backward in time. Think of it like hitting rewind on a video of a black hole's life. Instead of an infinitely dense point sucking everything in, you'd see a burst of energy and matter exploding outward. This isn't just poetic imagination, it's a serious mathematical possibility embedded in Einstein's equations of general relativity. Einstein's field equations describe how matter and energy shape the fabric of space-time, and the math doesn't just allow for black holes, it also permits their mirror opposites. If you plug in the numbers, white holes emerge as perfectly valid solutions, just with one crucial difference. Time flows in reverse inside them, but here's where things get tricky. While the equations suggest white holes could exist, the universe doesn't seem to play by those rules, at least not in any way we've observed. So why does this idea persist? Because it solves some of the biggest puzzles in physics. Take the singularity at the heart of a black hole, a point where the math breaks down and the known laws of physics stop making sense. Some physicists speculate that if a black hole could somehow reverse into a white hole, that singularity might never actually form. Instead, the collapsing star would rebound like a cosmic rubber band and spew everything it had swallowed back out. This leads us to the biggest question of all. Could white holes be real, or are they just mathematical ghosts? On paper, they're flawless, but in reality, we've never spotted one. The problem: white holes violate our everyday intuition about how things work. The second law of thermodynamics tells us that entropy disorder always increases over time. A white hole blasting out pristine energy seems to defy that. And yet, some theories in quantum gravity, like loop quantum cosmology, suggest that under extreme conditions, the rules might bend just enough to let white holes slip through. For now, they remain one of the most tantalizing what-ifs in astrophysics, a concept that challenges our understanding of time, energy, and the very nature of reality. And that's exactly what makes them so fascinating. They force us to ask, could the universe be far stranger than we've ever imagined? Next, we'll explore how white holes might be breaking one of physics' most sacred laws, and why some scientists think that's not as impossible as it sounds. Let's shift gears and tackle one of the most puzzling aspects of white holes: their apparent defiance of one of the universe's most unbreakable rules. The second law of thermodynamics is like the strict referee of physics. It states that in any closed system, entropy, a measure of disorder, must always increase over time. In simpler terms, things naturally tend to fall apart, not come together. Heat flows from hot to cold, never the other way around. Coffee cools down, it doesn't spontaneously reheat itself. But white holes, they seem to flip this idea on its head. Imagine a cosmic fountain gushing energy and matter into space without any visible source. Unlike black holes, which devour everything in their path, white holes would theoretically expel material with no obvious input. This creates a glaring contradiction. If energy can't be created or destroyed, only transformed, how does a white hole manage to spit out matter and radiation seemingly out of nowhere? It's like a magician pulling an endless stream of scarves from an empty hat, except in this case, there's no hidden trick, at least not one we understand yet. Physicists are deeply divided on whether this violation is a deal-breaker or just a clue that our current laws are incomplete. Some argue that white holes are simply mathematical curiosities, elegant solutions to equations that don't translate to reality. Others propose that in extreme conditions like those near the birth of the universe, the laws of thermodynamics might operate differently. For example, in loop quantum gravity, a leading theory aiming to bridge general relativity and quantum mechanics, white holes could emerge from the remnants of dying black holes, effectively recycling their energy without breaking the rules. Here's where it gets even more intriguing. If white holes do exist, they might not be eternal. Some models suggest they'd be incredibly unstable, exploding or collapsing almost instantly. This could mean their entropy-defying behavior is just a brief blip in the grand cosmic timeline, a momentary exception rather than a full-scale rebellion against physics. But even a fleeting white hole raises profound questions. Could the Big Bang itself have been a white hole event, a sudden release of energy from some unseen precursor? And if so, does that mean our entire universe is the product of a thermodynamic anomaly? The debate isn't just academic. If white holes are real, they'd force us to rewrite textbooks. They'd challenge our understanding of causality, energy conservation, and even the arrow of time. Yet for all the controversy, they remain a thrilling possibility, one that stretches the limits of what we think is possible. Up next, we'll see how white holes sneak into Einstein's equations, and why math alone might not be enough to prove they're out there. Now let's turn our attention to Einstein's field equations, the very backbone of general relativity, where white holes first emerged as a tantalizing mathematical possibility. These equations describe how matter and energy warp the fabric of space-time, dictating everything from planetary orbits to the bending of light. But here's the twist: when scientists solved these equations, they didn't just predict black holes. The math also spat out their theoretical opposites, white holes. The equations treat white holes as perfectly valid solutions, mathematical siblings to black holes with all the same parameters, mass, charge, and spin, just flipped in behavior. If a black hole is a one-way street into oblivion, a white hole, according to the math, would be a cosmic exit door with no entrance. Yet despite their elegant symmetry in theory, the real-world plausibility of white holes remains hotly debated. Why? Because while mathematics allows for their existence, nature doesn't always follow the chalkboard. Consider a simple analogy. Think of Einstein's equations like a recipe book. The recipes might allow for a cake that rises perfectly without any baking powder, but in practice that cake would collapse every time. Similarly, white holes satisfy the math, but the physical mechanisms to create them are baffling. How could a white hole form in the first place? Black holes are born from collapsing stars, but there's no known astrophysical process that would birth their radiant counterparts. This tension between math and reality isn't new. Physics is full of mathematically beautiful ideas that fail the test of observation. Take tachyons, hypothetical particles that always move faster than light. The equations permit them, but no one's ever spotted one. White holes face the same skepticism. Critics argue they're mere artifacts of the math, interesting quirks with no counterpart in the observable universe. But defenders counter that maybe we're just missing a piece of the puzzle. After all, Einstein's equations famously predicted black holes decades before we had any evidence they existed. Could white holes be awaiting their moment of discovery? Some theories suggest they might emerge from the quantum realm. In loop quantum gravity, for instance, a collapsing black hole might rebound into a white hole at microscopic scales, offering a potential pathway for their formation. The debate cuts to the heart of how science progresses. Do we dismiss white holes as mathematical fantasy, or do we keep searching for ways they might fit into the cosmos? For now, they remain enigmatic outliers, solutions without a clear problem, predictions without a smoking gun. Yet their persistence in the equations keeps the door open, inviting us to wonder if the universe might still have surprises up its sleeve. Up next, we'll examine an even more daring idea that the Big Bang itself could have been a white hole event, blurring the line between creation myth and cutting-edge physics. Now let's venture into one of the most mind-bending ideas in cosmology, the possibility that the Big Bang wasn't just the beginning of everything, but actually a white hole event. Imagine the universe's birth not as a fiery explosion from nothingness, but as a cosmic eruption spewing out matter and energy from a white hole's theoretical exit door. This hypothesis, though speculative, offers a radical twist on our origin story, blending the mysteries of white holes with the enigma of creation itself. Supporters of this idea point to some striking parallels. White holes, by definition, are regions where matter and energy can only pour outward, never inward, much like how the early universe rapidly expanded in all directions. The Big Bang singularity, a point of infinite density, eerily mirrors the theoretical core of a white hole, where physics as we know it breaks down. Some models even suggest that if a black hole's collapse could rebound into a white hole at quantum scales, then the entire universe might be the result of such a rebound on a colossal level. But this theory isn't without its critics. One major hurdle is the question of what, if anything, existed before the Big Bang. If it was a white hole, where did the material it ejected come from? Traditional cosmology sidesteps this by treating the Big Bang as the absolute beginning, but the white hole hypothesis drags us back into the murky waters of pre-Big Bang physics. Skeptics argue that without evidence of a prior spacetime framework or a mechanism to trigger such an event, the idea remains more poetic than provable. Another sticking point is entropy, the universe's tendency toward disorder. The Big Bang began in an incredibly low entropy state, a fact that puzzles scientists to this day. White holes, however, are thought to defy entropy by producing order from nothing, which seems to align with the Big Bang's initial conditions. But critics counter that this just replaces one mystery with another, asking how a white hole could naturally generate such precise, low entropy conditions without violating known thermodynamic laws. Despite these challenges, the hypothesis has gained traction in certain circles. Some quantum gravity theories, like loop quantum cosmology, suggest that the Big Bang could have been a quantum bounce from a previous universe's collapse, a scenario that loosely resembles a white hole's rebirth. Others propose that white holes might exist in a deeper layer of reality, like a hidden dimension or a parallel universe, making their effects detectable only indirectly. At its core, this debate forces us to confront the limits of our knowledge. The Big Bang as a white hole is a bold attempt to weave together two of physics' greatest puzzles: cosmic origins and the nature of singularities. Whether it holds up or not, the idea pushes cosmologists to rethink old assumptions and explore wild new possibilities. Up next, we'll tackle another cosmic conundrum: how white holes might offer a solution to the infamous black hole information paradox, where the rules of quantum mechanics clash with the destructive power of singularities. Now let's shift our focus to one of the most puzzling mysteries in modern physics, the black hole information paradox, and how white holes might hold the key to solving it. At first glance, black holes seem to erase information forever, swallowing everything from stars to light without a trace. But quantum mechanics insists that information can never truly be destroyed. So where does it go? This is where white holes enter the discussion, offering a daring solution. What if black holes don't destroy information but instead transform and eventually release it through a white hole? The paradox stems from a fundamental clash between general relativity and quantum mechanics. According to Einstein's theory, black holes are simply defined only by their mass, spin, and charge. Once something crosses the event horizon, it's gone for good, leaving no trace of its original form. But quantum mechanics says every particle carries information that can't just vanish. If black holes truly obliterate information, it would mean the universe is fundamentally unpredictable, undermining the core of quantum theory. Enter the white hole hypothesis. Some physicists suggest that when a black hole reaches the end of its life, it could transition into a white hole, effectively turning its exit-only nature into a cosmic recycling mechanism. Instead of information being lost forever, it would be encoded and later expelled like a cosmic hard drive, rebooting and spitting out scrambled data. This idea, while elegant, is highly speculative. No one knows how information might survive the crushing depths of a singularity or how it could re-emerge intact. Supporters of this theory point to quantum gravity models, which propose that black holes might not form true singularities, but instead reach a point where quantum effects cause a bounce. In this scenario, the black hole's collapse would reverse, creating a white hole that releases the trapped information over billions or even trillions of years. The process would be incredibly slow, explaining why we've never observed it. But mathematically, it offers a way to preserve information without breaking the laws of physics. Critics, however, raise tough questions. Even if white holes could expel information, how would it remain coherent after enduring such extreme conditions? The intense gravity of a black hole should scramble information beyond recognition, like shredding a book and tossing the pieces into a hurricane. Some argue that without a clear mechanism to restore order, the information would be meaningless, a solution in name only. Others question whether white holes, which remain purely theoretical, are just substituting one mystery for another. Despite the skepticism, the idea has intriguing implications. If white holes do preserve information, they could act as cosmic archives, storing the history of everything they've ever absorbed. This would mean the universe has a built-in backup system, ensuring no detail is ever truly lost. It's a tantalizing thought, especially for theories like the holographic principle, which suggests that all information in a region of space might be encoded on its boundary, a concept that aligns loosely with white hole behavior. For now, the paradox remains unsolved. White holes offer a compelling but unproven escape route, blending the weirdness of quantum mechanics with the enigmas of spacetime. Whether they're the answer or just another step toward a deeper truth, they push physicists to rethink how information, gravity, and quantum rules interact. Up next, we'll explore the elephant in the room. Why, if white holes exist, have we never seen one? The answer might lie in the very nature of these elusive cosmic phenomena. Now let's tackle the glaring question hanging over all this white hole speculation. If they're real, why haven't we spotted one yet? It's a mystery that even the most enthusiastic theorists can't ignore. After all, black holes were once just ink on paper until technology caught up and proved their existence. So where's the smoking gun for white holes? The answer lies in a mix of cosmic timelines, observational hurdles, and some downright strange physics. First, consider the sheer scale of time involved. If white holes truly are the reversed aftermath of black holes, they'd operate on timelines that dwarf human existence. A typical black hole might take longer than the current age of the universe to transition into a white hole, assuming it ever does. That means any white holes out there could be remnants of black holes formed in epochs so ancient, their rebirth is still centuries or millennia away from even beginning. We're essentially searching for phenomena that might not have even started their performance yet. Then there's the detectability problem. White holes, by definition, expel energy and matter outward. But unlike supernova or quasars, which flood space with unmistakable signals, a white hole's emissions could easily blend into the cosmic background. Imagine trying to spot a single firework in a sky already filled with auroras. Current telescopes and sensors aren't calibrated to distinguish white hole radiation from more mundane astrophysical events like gamma-ray bursts or neutron star collisions. Without a unique signature to latch onto, these cosmic exhaust vents might be hiding in plain sight. Some theorists propose an even wilder idea, that white holes, if they exist at all, might be inherently fleeting. Picture a burst of energy so rapid that by the time our instruments swing into position, the phenomenon has already vanished. This pop and fade model suggests white holes could appear and disappear in cosmic snapshots, leaving behind no trace except perhaps a brief, unexplained flare in distant galaxy surveys. It's like trying to photograph a lightning strike with a camera that takes minutes to focus. By then, the moment is long gone. Another hurdle is location. If white holes emerge from black holes, they'd likely form in the same isolated, lightless voids where their predecessors lurk. Black holes are famously shy, often detectable only by their gravitational effects on nearby stars or gas. A white hole embedded in such a desolate region would have few nearby particles to expel, making its outbursts faint or intermittent. It's the universe's worst game of hide and seek. We're searching for something that might not have anything to throw at us. But perhaps the most intriguing explanation is that we've already seen white holes and just didn't recognize them. Some astronomers argue that certain ultra-high-energy cosmic rays or puzzling gamma-ray flashes could fit white hole models. Take the infamous fast radio bursts, brief, intense blasts of radio waves from deep space. While most attribute these to magnetars or colliding neutron stars, a handful of researchers speculate they might align with white hole emissions. The challenge proving it, without a way to peer beyond these transient events, they remain cosmic Rorschach tests open to interpretation but impossible to confirm. So where does that leave us? For now, the absence of observed white holes doesn't disprove them. It simply underscores how alien their behavior might be compared to the astrophysical phenomena we're used to studying. But the search isn't over. Next-generation telescopes like the Vera Rubin Observatory or space-based gravitational wave detectors might finally catch a glimpse of these elusive objects. Until then, their invisibility remains one of the universe's most tantalizing open questions. Up next, we'll dive into how cutting-edge quantum gravity theories are breathing new life into the white hole hypothesis, and why math alone might not be enough to settle the debate. Now let's shift our gaze to a realm where the rules of gravity itself get rewritten: quantum gravity theories. While general relativity paints white holes as elegant mathematical possibilities, quantum gravity frameworks like loop quantum cosmology dare to ask, could these cosmic enigmas be more than just equations on a blackboard? The answer might lie in the tiny, frenetic world of the quantum scale, where space and time behave in ways that defy everyday intuition. Loop quantum cosmology, a leading contender in the quest to unify quantum mechanics and gravity, offers a radical twist on the white hole story. In this model, the crushing density of a collapsing star doesn't culminate in a singularity, a point of infinite curvature that spells doom for physics as we know it. Instead, quantum effects at unimaginably small scales create a repulsive force, causing the collapsing matter to bounce back outward. Picture a rubber ball hitting the ground so hard it rebounds upward, but in this case the ball is an entire star, and the ground is a quantum barrier we're still struggling to understand. This bounce, according to the theory, could birth a white hole, a region where matter and energy erupt back into the universe rather than vanishing forever. What's fascinating here is the timeline. Unlike classical relativity's prediction that black holes take eons to potentially transition into white holes, loop quantum cosmology suggests the process could be startlingly fast. Calculations hint that a stellar mass black hole might transform into a white hole within milliseconds from its own perspective, though outside observers caught in the warped flow of time near the event horizon would perceive it taking far longer. This discrepancy isn't a flaw, it's a feature of how relativity and quantum mechanics clash at these extremes. It also means that if this theory holds, white holes might not be the eternally dormant relics we imagined, but fleeting, explosive events scattered throughout cosmic history. But loop quantum cosmology isn't the only framework playing with white holes. Another approach, called asymptotic safety in quantum gravity, proposes that at extremely high energies, gravity itself changes nature, becoming what physicists call renormalizable. Without diving too deep into the math jargon, this essentially means that under these extreme conditions, the fabric of spacetime might smooth out singularities, replacing them with dense but finite objects. In some versions of this theory, a black hole's interior could tunnel through quantum spacetime into a white hole's exterior, like a wormhole with a built-in reset button. The catch: these models rely on speculative mathematics that hasn't yet been tested or even fully developed. Then there's string theory, the famously complex theory of everything candidate. Some string theorists argue that white holes could be dual to black holes in higher dimensional space, linked through hypothetical membranes called branes. Imagine our universe as a sheet of paper floating in a higher dimensional void. A black hole puncturing the sheet from one side might manifest as a white hole piercing through from the other. While mathematically intriguing, this idea is currently untestable, leaving it in the realm of dazzling conjecture. The real hurdle for all these theories is bridging the gap between elegant math and observable reality. Quantum gravity frameworks excel at resolving the singularities that break classical physics, but they struggle to make concrete predictions about what white holes would actually look like through a telescope. Would they emit a distinctive spectrum of light? Could they leave gravitational wave fingerprints? Without these observational hooks, white holes remain trapped in theoretical limbo. Yet the pursuit matters deeply. If quantum gravity can successfully describe white holes, it wouldn't just validate their existence, it would revolutionize our understanding of spacetime's fundamental nature. These theories suggest that at the smallest scales, space isn't smooth and continuous but granular, like a digital image zoomed in until pixels appear. White holes, in this view, might be glitches in that pixelated framework, moments where the universe's underlying code hiccups and reboots. As we edge closer to experiments that could probe these ideas, like atom interferometers measuring minuscule spacetime fluctuations or gravitational wave detectors hunting for quantum echoes, the dream of witnessing a white hole feels less like sci-fi and more like a tomorrow possibility. Up next, we'll explore an electrifying offshoot of these theories, the whispers in gravitational wave data that some believe could be white holes calling from the cosmic deep. Now let's turn our attention to something that sounds like it's straight out of a cosmic detective story: the strange whispers in the aftermath of black hole collisions. When two black holes spiral into each other and merge, they don't just vanish quietly. They send ripples through spacetime itself, gravitational waves that detectors like LIGO and Virgo have been catching for years. But buried in those ripples, some physicists believe there might be hidden clues pointing to something even wilder: white holes. Here's how the idea works. When black holes collide, the event sends out gravitational waves in a specific pattern, an initial burst as they merge, followed by a ring-down phase where the new, larger black hole settles into its final shape. But a handful of researchers claim they've spotted something odd in the data: tiny, repeating signals trailing the main event like echoes in a cave. These echoes, if real, don't fit the standard black hole picture. Instead, they match what you'd expect if the black hole's event horizon wasn't the one-way street we thought it was, but had a hidden backdoor, a white hole remnant. Think of it like dropping a pebble into a pond. Normally, you'd see the ripples spread out and fade, But if the pond had an invisible barrier that bounced some of those ripples back, you'd see faint, delayed echoes. In this case, the barrier isn't in water but in the fabric of space-time near the black hole. If quantum effects near the event horizon create a repulsive force, similar to the bounce in loop quantum cosmology, some gravitational waves could ricochet back out, creating those elusive echoes. Not everyone's convinced, though. Critics argue these signals could be noise in the detectors or artifacts of data processing. After all, gravitational wave astronomy is still in its infancy, and teasing faint echoes from the cosmic static is like trying to hear a whisper in a hurricane. Even the teams who first reported the echoes admit the evidence is tentative, calling for more sensitive detectors and better analysis methods to confirm or rule them out. But if the echoes are real, the implications are staggering. They'd suggest that black holes don't end as eternal prisons but transform into white holes over time, not in the trillion-year time frame of Hawking radiation, but almost instantly from an outside observer's perspective. This would mean every black hole collision could secretly be a white hole in disguise, spewing energy and information back into the universe in subtle, quantum-sized bursts. What makes this hypothesis so tantalizing is that it's testable, at least in principle. Future upgrades to gravitational wave observatories, like the planned LISA mission in space, could have the precision to spot these echoes definitively. Some researchers are even developing algorithms to comb through existing data for more echo candidates, treating the universe like a vast crime scene where white holes might have left fingerprints. The echo hypothesis sits at the crossroads of two revolutionary ideas: quantum gravity and observational astrophysics. If confirmed, it wouldn't just add white holes to the cosmic menagerie. It would force us to rewrite the textbook on how black holes live, die, and perhaps rebirth themselves. Until then, these echoes remain ghostly hints, teasing us with the possibility that the universe's most destructive phenomena might also be its most creative. Next, we'll venture into even more speculative territory, a theory that casts white holes as the invisible architects of the cosmos itself, hiding in plain sight as the mysterious dark matter that shapes galaxies. Now let's shift gears to one of the most audacious ideas in modern cosmology: the possibility that white holes might be hiding in plain sight as the universe's missing dark matter. It's a radical proposal, but in a puzzle as baffling as dark matter, sometimes the wildest guesses lead to breakthroughs. For decades, astronomers have known that something invisible, something that doesn't emit, absorb, or reflect light, exerts enough gravity to sculpt galaxies and bend space-time itself. We call this mystery substance dark matter, and despite overwhelming indirect evidence, no one's ever detected it directly. That's where white holes enter the conversation. Could these theoretical cosmic geysers, spraying energy outward instead of sucking it in, be the dark matter we've been searching for? Here's the bold reasoning behind the idea. If white holes exist, they'd be nearly impossible to spot directly. Unlike black holes, which betray their presence by tearing apart stars or glowing with X-rays as they feed, white holes, by definition, don't consume matter. They'd just sit there, invisible, occasionally burping out radiation or particles. But gravity doesn't discriminate. Whether an object is dark or glowing, if it has mass, it warps space-time. So if the universe is peppered with ancient white holes left over from the Big Bang or quantum processes, their collective gravity could mimic the effects we attribute to dark matter. Proponents of this theory point to a few intriguing clues. Some models suggest white holes could form microscopic, primordial versions in the extreme conditions of the early universe, potentially numbering in the trillions per cubic light year. These tiny white holes wouldn't emit much energy individually, but their combined mass could add up to the missing gravitational pull we observe. There's also the curious fact that dark matter seems to cluster in halos around galaxies, just as you'd expect if white holes were scattered relics from cosmic dawn, lingering where gravity has pooled them over billions of years. But before we rewrite the textbooks, let's talk about the elephant in the room, the colossal challenges this idea faces. First, white holes, as we understand them, aren't stable. Most solutions to Einstein's equations show them exploding or collapsing almost instantly. For white holes to persist as dark matter, they'd need some unknown physics to keep them from vanishing. Second, even if they existed, their emissions, however faint, should leave traces in cosmic background radiation or high-energy particle streams. So far, no such signal has been found. Then there's the sheer weirdness of the proposal. Dark matter appears to interact gravitationally in ways that suggest it's smoothly distributed, not clumpy like discrete objects. If white holes were the answer, they'd need to be so numerous and evenly dispersed that they'd effectively mimic a continuous substance, a tall order for objects that, by nature, would likely be isolated and rare. Skeptics also highlight that white holes don't solve dark matter's smaller-scale puzzles, like the cusp core problem, where galaxies seem less dense at their centers than simulations predict. Traditional dark matter particles can explain this via subtle interactions, but white holes as gravitational point sources struggle to account for it. Still, the idea refuses to die entirely, partly because dark matter's true nature remains elusive. Every failed search for exotic particles like WIMP or actions leaves room for alternative explanations. And here's the kicker. If future gravitational wave detectors or quantum gravity experiments found evidence for white holes, it would force us to reconsider their role in the dark matter saga. Until then, though, the theory remains a fascinating but fringe possibility, a reminder that in cosmology, sometimes the most outrageous ideas are worth a second look. Up next, we'll dive into an even more speculative link, one that ties white holes to the sci-fi dream of interstellar shortcuts, as we explore their hypothetical connection to wormholes. Now let's venture into one of the most tantalizing what-ifs in theoretical physics, the idea that white holes could be gateways to wormholes, threading the universe with cosmic shortcuts. It sounds like pure science fiction, but the math doesn't outright dismiss it. In fact, some solutions to Einstein's equations hint at a bizarre kinship between these two phenomena, suggesting they might be two sides of the same spacetime marvel. Imagine a wormhole as a tunnel through the fabric of the universe, connecting distant points in the blink of an eye. For decades, physicists like Kip Thorne have toyed with the notion that such tunnels could exist, but there's always been a catch. Wormholes, as we model them, are incredibly unstable. They'd snap shut instantly unless propped open by something with negative energy, a hypothetical substance that defies everyday physics. That's where white holes come in. Here's the provocative twist. Some theories propose that a white hole could act as the exit of a wormhole, while a black hole serves as the entrance. Picture this: matter falls into a black hole, squeezed to infinite density at the singularity, but instead of vanishing, it erupts out of a white hole somewhere else in the cosmos. If this cosmic plumbing held together, it wouldn't just bridge space, it could bridge time. A black hole's crushing gravity slows clocks to a crawl near its event horizon, while a white hole's explosive output might speed them up. The result, a tunnel where the exit exists in another time entirely. But before we pack our bags for Andromeda, let's ground this in reality. The white hole wormhole link hinges on a specific, ultra-rare solution to Einstein's equations called an Einstein-Rosen bridge. These bridges are mathematically possible, but they're catastrophically fragile. Pass even a single photon through one, and the tunnel collapses. That's why theorists speculate about exotic matter, a substance with negative energy density that could counteract this instability, propping the wormhole open like a scaffold. The trouble, exotic matter has never been observed, and many physicists argue it can't exist without violating known laws. Even if we ignore that hurdle, white hole wormholes pose another puzzle. How would anything survive the trip? Black holes shred matter with tidal forces long before it reaches the singularity, while white holes blast it outward with unfathomable energy. Unless some undiscovered physics smooths this cosmic gauntlet, travelers would be atomized in transit, yet the dream persists, fueled by intriguing loopholes. Quantum mechanics, for instance, allows for microscopic wormholes that flicker in and out of existence at the smallest scales. Some researchers suggest these quantum tunnels might be stabilized by white hole-like effects at their endpoints, though scaling them up to human proportions remains pure fantasy. Others speculate that advanced civilizations capable of manipulating space-time itself might engineer wormholes using white holes as anchors. It's a stretch, but in a universe where 95% of everything is dark energy and dark matter, who's to say what's impossible? The most sobering reality check comes from observation, or rather, the lack of it. If white hole wormholes dotted the cosmos, their emissions would be unmistakable. We'd expect to see bursts of high-energy particles or light with no obvious source, like cosmic fireworks marking their exits. So far, no such smoking gun has turned up. Still, the white hole wormhole connection lingers in the scientific imagination, not just as a tool for interstellar travel, but as a lens to probe gravity's deepest secrets. If wormholes exist, they'd warp space-time so severely that they'd challenge our understanding of causality, quantum mechanics, and the very nature of reality. And if white holes are their other mouths, discovering one could rewrite the rules of the universe. As we'll see next, this speculative leap from equations to starships underscores how white holes blur the line between hard science and hopeful speculation. But that's the thrill of cosmology sometimes. The wildest ideas light the path to truth. Now let's step out of the equations for a moment and into the realm of imagination. Science fiction has long been fascinated by the idea of white holes, often spinning them into grand cosmic gateways or time-bending anomalies. But how do these dramatic portrayals stack up against the cold, hard math of theoretical physics? The truth is, while Hollywood loves to take liberties, the real science behind white holes is captivating enough on its own, just in very different ways. Take the 1979 Disney film The Black Hole, for example. While it doesn't feature a white hole directly, it plays with the idea of black holes as portals to other dimensions, a trope that often bleeds into white hole speculation. In the movie, characters emerge from a black hole unharmed, stepping into a surreal, mystical realm. In reality, crossing a black hole's event horizon would mean certain doom, spaghettification, crushing gravity, and no chance of escape. White holes, if they exist, wouldn't offer a gentler exit either. Their violent outpourings of energy would make them more like cosmic geysers than serene doorways. Then there's the Stargate franchise, where wormholes, often conflated with white holes in pop culture, serve as instant highways between planets. The show handwaves the science with fictional stargates, but real white holes wouldn't function as neatly. Unlike the stable, user-friendly portals on screen, a natural white hole wormhole system would be chaotic, unstable, and likely lethal. No handy dialing device, no smooth transit, just a maelstrom of physics-defying extremes. Even Interstellar, praised for its scientific accuracy, took creative license. The movie's black hole, Gargantua, leads characters to a higher dimensional tesseract where time becomes malleable. While white holes weren't part of the plot, the film's blend of real relativity and speculative filler mirrors how sci-fi often merges fact and fantasy. In truth, white holes don't offer neat access to alternate dimensions or time loops. At best, they're hypothetical exhaust pipes for black holes, with no evidence they'd enable the kind of narrative shortcuts writers adore. So where does fiction diverge most sharply from theory? First, the idea of survivability. Sci-fi loves to send heroes through cosmic anomalies unharmed, but real white holes would be anything but hospitable. Their theoretical energy output rivals gamma ray burst some of the most violent events in the universe. Second, control. Movies often depict these phenomena as tools or weapons, like Event Horizon's hellish gateway or Doctor Who's time-warping, white hole-powered engines. In reality, white holes aren't machines to be switched on or off. They'd be natural, uncontrollable, and governed by laws we barely understand. That said, science fiction isn't just about getting the physics right, it's about sparking curiosity. While Star Trek's warp drives and Contact's wormhole travel aren't accurate, they've inspired generations of scientists to ask, could we? And in that sense, white holes serve a vital role in fiction. They stretch our imagination, giving us a sandbox to play with ideas before math and observation weigh in. The takeaway: white holes in fiction are fun, thrilling, and often beautiful, but they're not documentaries. The real theories behind them are far stranger and more constrained by the unforgiving rules of the cosmos. Yet both realms, science and sci-fi, share one crucial goal: to explore the unknown. And whether through equations or escapism, they remind us that the universe's deepest mysteries are still waiting to be unraveled. Up next, we'll shift gears to a theory that's equally mind-bending but rooted in cutting-edge math: the idea that collapsing stars might not form black holes at all, but instead rebound as white holes in a spectacular cosmic bounce. Stepping beyond the realm of science fiction, let's dive into one of the most radical ideas in theoretical physics: the possibility that dying stars might not form black holes at all, but could instead rebound as white holes in a dramatic cosmic reversal. This is the quantum bounce hypothesis, a concept that turns our traditional understanding of stellar collapse on its head. Here's how it challenges the conventional story. When a massive star exhausts its nuclear fuel, gravity takes over, crushing it inward. According to classical physics, this collapse is unstoppable, leading to a singularity, a point of infinite density where the laws of physics break down. But quantum mechanics, the rules governing the very small, suggests there might be a twist. Instead of vanishing into a black hole's singularity, the star could hit a quantum wall, a point where gravity's crush is counteracted by repulsive quantum forces. Picture a rubber ball hitting the ground with enough force to bounce back up. In this scenario, the star's collapse would reverse, erupting outward as a white hole, a cosmic rebirth instead of a grave. The math behind this idea emerges from loop quantum gravity, a framework that attempts to unify quantum mechanics with general relativity. In this model, spacetime isn't smooth and infinitely divisible but granular, woven from tiny loops. At extremely high densities, these loops generate a repulsive force strong enough to halt a singularity's formation. Proponents argue this could transform a black hole's core into a white hole's engine, spewing out the star's remnants over billions of years. But why haven't we seen this happen? For one, the timescales are mind-bending. A black hole to white hole transition, if it occurs, might take longer than the current age of the universe to unfold from an outside observer's perspective. To us, the star would still appear as a black hole, its potential white hole phase lingering far in the future. There's also the energy problem. A white hole born from a bounce would release an unimaginable burst of radiation, something we'd expect to notice. Yet no such events have been conclusively observed. Critics raise another hurdle: the information question. If a black hole becomes a white hole, what happens to all the matter and energy it swallowed? Would it be scrambled beyond recognition or spat back out intact? Some models suggest the white hole's output could encode the original star's information, offering a neat solution to the black hole information paradox. Others argue the process would be too messy to preserve meaningful data. Despite the uncertainties, the quantum bounce idea is tantalizing because it sidesteps the need for singularities, those infinitely dense points that physicists loathe because they defy explanation. If correct, it would mean the universe has a built-in safety valve against infinite collapse, recycling doomed matter into something new. It's a poetic twist, death and rebirth written into the fabric of reality itself. As we push the boundaries of observation, from gravitational wave detectors to next-gen telescopes, we might one day catch hints of this cosmic rebound in action. Until then, the quantum bounce remains a beautiful, unproven melody in the symphony of theoretical physics, a reminder that even the most extreme corners of the universe might still hold surprises. Now, let's turn to an even more abstract frontier, where white holes aren't just stellar phenomena but potential keys to understanding the universe as a giant hologram. Now let's stretch our imaginations even further and explore how white holes might fit into one of the most mind-bending ideas in modern physics, the holographic principle. This concept suggests that our entire three-dimensional universe could actually be a projection of information stored on a two-dimensional surface, like a cosmic hologram. And if that's true, white holes might play a surprising role in this grand cosmic code. The holographic principle emerged from attempts to solve a puzzle about black holes. When matter falls into a black hole, it seems to vanish, but quantum mechanics insists information can't be destroyed. So where does it go? The answer, according to theorists like Leonard Susskind, is that all the information about what's inside a black hole gets encoded on its event horizon, the point of no return. Think of it like a DVD surface containing the data for a full 3D movie. The universe might work the same way, with a true reality existing on distant boundaries we can't see. So where do white holes come in? If black holes encode information on their surfaces, white holes, theorized as their time-reversed twins, might be the decoders. Imagine a white hole as a cosmic projector, taking that compressed information and playing it back into the universe. Some models suggest that when a black hole transitions into a white hole, it doesn't just spit out random energy. It could be reconstructing the original information it swallowed, like a cosmic printer reassembling shredded documents. This gets even stranger when you consider the holographic universe's implications for space itself. If our 3D world is just a shadow of 2D data, then white holes might be glitches or overflow points in that code. Picture a computer simulation hitting a processing limit and creating an emergency output valve. A white hole could be nature's way of preventing information overload, ensuring the cosmic hologram doesn't crash. But there's a catch. For the holographic principle to work with white holes, they'd need to obey the same information-preserving rules as black holes. That's tricky because white holes seem to generate energy and information out of nowhere, a potential violation of quantum laws. Some physicists argue this could mean white holes are inherently unstable, flickering in and out of existence too quickly to observe. Others propose that white holes might only activate when the universe's underlying code demands it, like a fail-safe mechanism, the most tantalizing idea. If the holographic principle is correct, white holes might not just be cosmic oddities, they could be evidence of a deeper layer of reality. Just as a hologram reveals hidden dimensions when you tilt it, white holes might be glimpses of the universe's true, encoded nature. Future experiments, like ultra-precise measurements of spacetime's granularity, could look for signatures of this holographic pixelation near white hole analogs. While this sounds like science fiction, remember that black holes were once purely theoretical too. The holographic principle, as wild as it seems, is a serious framework tested through black hole thermodynamics and string theory. White holes, if they exist, might be the missing puzzle piece showing how information flows in this cosmic projection, turning the universe into the ultimate holographic display. Now let's confront one of the most baffling puzzles surrounding white holes, the energy paradox. If white holes truly exist, their behavior flips everything we know about energy conservation on its head. According to theoretical models, these cosmic oddities don't just emit energy, they could, in principle, unleash infinite amounts of it. That's not just strange. That's a direct challenge to the fundamental laws of physics as we understand them. First, let's break down why white holes are theorized to be such energy powerhouses. Unlike black holes, which pull everything in, white holes eject matter and energy relentlessly. Picture a fire hose blasting water at full force, but instead of water, it's spewing out radiation, particles, and perhaps even entire galaxies worth of material. Some solutions to Einstein's equations suggest this outburst wouldn't have a natural stopping point. The white hole could keep pouring out energy forever with no clear source fueling it. This is where physicists raise their eyebrows, because energy can't just appear from nowhere. Here's the core of the paradox. Our universe operates on strict rules, like the conservation of energy, which states energy can't be created or destroyed, only transformed. Yet white holes, as mathematical constructs, seem to break this rule effortlessly. Imagine finding a magical faucet that pours out unlimited water without being connected to any pipes. Scientists would call that impossible, and for good reason. The same skepticism applies to white holes. If they truly emitted infinite energy, they'd destabilize the cosmos, flooding it with radiation and warping the fabric of spacetime itself. So why do some models predict this infinite output? It ties back to the idea of white holes being the time-reversed versions of black holes. A black hole singularity crushes matter into an infinitely dense point. Flip that process in time, and a white hole singularity would theoretically explode outward with infinite energy. But here's the catch: infinity isn't just a big number. It's a concept that, when applied to real physics, often signals a flaw in our equations rather than a feature of nature. When infinities pop up in models, it usually means we've hit the limits of our current understanding. Critics argue this infinity problem is a death knell for white holes. After all, we've never observed anything in the universe with infinite energy output, not even close. Even the most violent cosmic events like supernovas or quasars operate within measurable energy budgets. Supporters, though, propose workarounds. Maybe white holes self-regulate, ejecting energy in finite bursts before shutting down. Or perhaps their emissions only appear infinite in simplified models, while a more complete quantum gravity theory would cap the energy outflow. Some even suggest white holes could borrow energy from parallel universes or hidden dimensions, though that strays deep into speculative territory. The energy paradox also raises a practical question. If white holes blasted infinite energy, why hasn't the universe been obliterated by one? One chilling hypothesis is that white holes, if they ever existed, were mostly an early universe phenomenon. They might have erupted violently during the Big Bang's aftermath, their energy diluted over billions of years into the cosmic background we see today. Alternatively, they could be so rare or short-lived that spotting one is like finding a single grain of sand in a desert. For now, the infinite energy problem remains a major roadblock for taking white holes from math to reality. But it's also a tantalizing clue. Physics thrives on paradoxes. They push us to refine our theories. The black hole information paradox, for instance, led to breakthroughs like the holographic principle. Similarly, wrestling with white holes' impossible emissions might reveal gaps in our grasp of quantum gravity or spacetime itself. Until then, these cosmic enigmas remind us that the universe still holds mysteries no equation can yet tame. Now let's venture beyond mainstream physics and explore how white holes fit into some of the most daring alternative cosmologies out there. While traditional models struggle to explain these cosmic anomalies, a handful of bold theories embrace white holes as essential pieces of the universe's puzzle, though not without controversy. Take the idea of a cyclic universe, for example. This radical model suggests our cosmos doesn't have a single beginning or end, but instead goes through endless cycles of expansion and contraction. In this view, a white hole could be the rebirth of a black hole from a previous cosmic cycle. Imagine a black hole from an earlier universe collapsing inward, only to rebound as a white hole in ours, spewing out matter and energy that seeds new galaxies. It's a poetic idea, suggesting white holes aren't just oddities but midwives of cosmic renewal. Yet here's the catch: cyclic models require conditions that violate known physics, like reversing entropy, which most scientists dismiss as untestable speculation. Then there's the black hole to white hole transition theory, popularized by loop quantum gravity. This framework proposes that when black holes reach the end of their lifespan, they don't vanish but instead quantum bounce into white holes. Picture a collapsing star hitting a sort of cosmic trampoline. Instead of forming a permanent singularity, it rebounds outward in a spectacular reversal. Proponents argue this avoids the pesky infinities plaguing classical models, but critics point out we've never observed such a transition, making it more mathematical wishful thinking than proven science. Some alternative cosmologies go even further, weaving white holes into grand narratives of parallel universes. In certain multiverse hypotheses, white holes act as bridges between disconnected realms, funneling matter and energy from one reality to another. Think of them as cosmic subway tunnels shuttling material between universes. While thrilling, these ideas often rely on unproven concepts like extra dimensions or exotic matter, leaving them firmly in the realm of theoretical playgrounds rather than testable science. Perhaps the wildest twist comes from proponents of emergent gravity, who suggest white holes might not even be objects but illusions, temporary glitches in spacetime's underlying code. In this digital physics-inspired view, white holes could be cosmic error messages, brief flickers where the universe's rules temporarily misfire. It's a fringe take, but it highlights how far alternative cosmologies stretch to explain or explain away these enigmatic entities. The common thread: most alternative cosmologies treat white holes as patchwork solutions to deeper theoretical gaps. They're compelling precisely because mainstream physics can't yet account for them cleanly. But credibility remains a hurdle. Without observational evidence or predictive power, these models often feel more like philosophical thought experiments than actionable science. Still, they serve a vital purpose, stretching our imaginations and testing the boundaries of what's possible. After all, today's heresy sometimes becomes tomorrow's textbook material. Just ask Galileo. What makes white holes so irresistible to alternative theories is their sheer audacity. They defy intuition, challenge dogma, and invite us to rewrite cosmic rules. Whether any of these daring ideas hold water remains to be seen, but one thing's certain: in the quest to understand white holes, even the wildest theories remind us that the universe is far stranger than we dare suppose. Now let's dive into a fiery cosmic paradox that could reshape how we see white holes. The white hole firewall problem is one of the most mind-bending debates in theoretical physics, and it mirrors a similar controversy swirling around black holes. Picture this: as matter and energy erupt from a white hole's boundary, some models suggest an invisible wall of searing radiation might form there, a barrier so intense it could vaporize anything trying to cross. This idea stems from a thorny issue in black hole physics known as the firewall paradox. Back in 2012, physicists argued that the event horizon of a black hole might not be the smooth gateway Einstein predicted, but instead a violent zone of high-energy particles. The same logic could apply to white holes. If information trapped in a black hole escapes when it becomes a white hole, the process might create a firewall at its boundary, a cosmic shredder ensuring nothing gets in or out unscathed. Why would such a firewall exist? It all ties back to quantum mechanics and the clash between two fundamental principles. On one hand, quantum theory says information can't be destroyed, so if a black hole swallows particles, their data must eventually re-emerge, perhaps via a white hole. On the other hand, Einstein's relativity insists spacetime near a white hole's boundary should be smooth and uneventful for an observer falling toward it. The firewall is the unsettling compromise, a blistering layer that preserves information but tortures anything encountering it. Here's where things get even stranger. For white holes, firewalls could be even more extreme than their black hole counterparts. Since white holes expel rather than absorb matter, their firewalls might not just burn incoming objects, they could also amplify outgoing radiation to staggering energies. Imagine a cosmic particle accelerator built into spacetime itself, blasting energy with forces we've only seen in particle colliders or supernova. Yet the firewall idea is far from settled science. Critics argue it's a sign that our theories are incomplete, not a real physical phenomenon. Some propose alternatives like fuzzballs in string theory, where white holes have tangled, fuzzy surfaces instead of fiery walls. Others suggest firewalls are mirages, tricks of perspective that vanish if we account for quantum entanglement properly. What's at stake isn't just whether white holes have firewalls, but whether our understanding of spacetime's fabric holds up under extreme conditions. If firewalls are real, they'd force us to rewrite Einstein's rules near white holes. If they're not, we'd need a radical new way to reconcile quantum mechanics and gravity. Either way, this debate proves white holes aren't just mathematical oddities, they're cosmic stress tests for physics itself. Now consider the implications. If a white hole firewall exists, it could explain why we've never detected one. Anything venturing near might be obliterated before sending signals back to us. Or perhaps firewalls are fleeting, flickering in and out of existence during a white hole's brief lifespan. The mystery keeps theorists on their toes, probing deeper into how the universe handles its most extreme exits. This fiery puzzle reminds us that white holes aren't passive cosmic drains, they're potential infernos, challenging everything we know about space, time, and the limits of reality. Whether firewalls stand or fall, their very possibility forces physics to confront its most thrilling unknowns. Shifting our focus to time itself, white holes present a puzzle that could turn our understanding of causality upside down. The arrow of time, that familiar one-way flow from past to future, might not be so straightforward in the presence of these cosmic oddities. White holes challenge this fundamental concept because they appear to run time backward compared to black holes. Where a black hole pulls matter in, never to return, a white hole pushes matter out, as if rewinding the process. This reversal isn't just about matter. It suggests time near a white hole might flow in the opposite direction we're used to. The key to this mystery lies in entropy, the measure of disorder in a system. Normally, entropy always increases, giving time its direction. But white holes, by spewing out perfectly ordered energy and matter, seem to decrease entropy locally. It's like watching a shattered vase reassemble itself, a violation of everything we know about time's natural flow. This isn't just theoretical hand-waving. The mathematics of general relativity actually allows for these time-reversed solutions. Einstein's equations work equally well whether time runs forward or backward, but our everyday experience only shows us one direction. White holes force us to confront the possibility that time's arrow might be flexible under extreme cosmic conditions. The implications ripple through physics. Causality, the principle that causes must precede effects, gets shaky near white holes. If time flows differently there, could an event's effect actually happen before its cause? Some models suggest white holes might briefly create these backwards in time scenarios before quantum effects correct them. Interestingly, this connects to one of white holes' proposed origins, the quantum bounce theory. When a dying star collapses, quantum gravity might reverse the process at the last instant, creating a white hole where time effectively runs in reverse from our perspective. The dying star's future becomes the white hole's past, yet nature seems to resist such time reversals. The absence of observed white holes might hint that the universe enforces a strong arrow of time, preventing large-scale reversals of entropy. Or perhaps we're simply not recognizing them. What looks like a cosmic explosion to us might be a white hole's beginning from its own time-reversed viewpoint. This temporal weirdness isn't purely academic. If white holes exist with reversed time flow, they could serve as natural time machines in theory. An observer crossing from a black hole to its white hole counterpart might experience time running backward relative to the outside universe. Of course, the firewall problem and other hurdles make this unlikely in practice. The white hole time puzzle ultimately teaches us something profound. Time's arrow may not be as universal as we thought. What seems like an inviolable law in our everyday lives, that eggs don't unscramble and memories only form of the past, might just be a local feature of our cosmic neighborhood. Beyond certain extreme boundaries, time could dance to a very different rhythm. As we ponder these possibilities, we're reminded that white holes aren't just space oddities. They're temporal anarchists challenging one of our most deeply held intuitions about how reality works. Whether they actually reverse time or merely mimic its effects, their existence would force physics to grapple with questions we've barely begun to ask. This brings us to an equally fascinating frontier: the role white holes might play in connecting parallel universes, a concept that stretches our imagination even further. Now let's stretch our imagination even further into the realm of parallel universes. White holes might not just be cosmic oddities in our universe, they could serve as gateways to entirely separate realities. This idea emerges from cutting-edge theories suggesting that white holes might connect to the multiverse, a hypothetical collection of alternate universes with their own physical laws and histories. The connection arises from the peculiar nature of white holes. If a black hole singularity leads not to destruction but to a white hole in another universe, as some models suggest, then these objects could act as tunnels between worlds. Imagine it like a cosmic subway system, where black holes are the entrances and white holes the exits. Only instead of traveling between neighborhoods, you'd be hopping between universes. This idea aligns with the concept of an Einstein-Rosen bridge, better known as a wormhole, but with white holes playing a starring role. Some physicists speculate that the Big Bang itself might have been a white hole eruption from another universe. In this scenario, our entire cosmos could be the other side of a black hole collapsed somewhere else in the multiverse. It's a staggering thought. Every star, planet, and galaxy we see might have emerged from a white hole birth in a parent universe. This would mean universes could reproduce, with black holes giving rise to new ones through white hole emissions, a process sometimes called cosmic natural selection. Quantum mechanics adds another layer to this multiverse link. The many worlds interpretation suggests every quantum event spawns parallel realities, and white holes could provide the physical mechanism for these branches. A particle entering a black hole in one universe might exit via a white hole in another, effectively splitting reality into multiple timelines. While this remains speculative, it offers a tantalizing way to unite quantum weirdness with cosmic-scale phenomena. But how would this actually work? One theory proposes that white holes could form the endpoints of wormholes threading through higher dimensional space. Just as a straw's opening appears as a circle in our three-dimensional world, but is really part of a longer tube, a white hole might be our limited view of a structure extending into another universe. Advanced versions of string theory even suggest that colliding white holes could create entirely new space-time geometries, birthing fresh universes with different fundamental constants. Critics point out major hurdles, of course. The energy required to sustain a traversable wormhole between universes would likely be prohibitive, and quantum gravity effects might collapse any such bridge instantly. Plus, if white holes really connected universes, we might expect to see exotic particles or energy signatures from elsewhere, something no telescope has detected. Yet the absence of evidence doesn't rule out the possibility, especially if these connections are rare or short-lived. The multiverse angle also reshapes the white hole information paradox. If information swallowed by black holes resurfaces via white holes in other universes, it neatly sidesteps the problem of lost data, though at the cost of making that information forever inaccessible to us. Some researchers argue this could explain why white holes seem so elusive in our universe. Their most dramatic effects might be happening elsewhere in the multiverse. Even if the multiverse remains unproven, white holes offer a compelling way to conceptualize it. They transform from cosmic curiosities into potential architects of reality, stitching together the fabric of multiple existences. Whether as cosmic umbilical cords linking parent and baby universes or as quantum portals between alternate timelines, their theoretical role in multiverse cosmology is as profound as it is puzzling. So while we've yet to find proof of parallel worlds, white holes keep the doorway tantalizingly ajar. One more reason these enigmatic objects continue to captivate scientists and dreamers alike. Next, we'll examine how white holes confront one of general relativity's most cherished principles, the concept of cosmic censorship. Now, let's turn our attention to one of the most intriguing puzzles in theoretical physics, how white holes might challenge the very fabric of cosmic order. The idea of cosmic censorship has long been a cornerstone of general relativity, a kind of cosmic rulebook that keeps the universe's most extreme phenomena hidden from view. But white holes could tear that rulebook apart by exposing what should never be seen: naked singularities. Roger Penrose, the brilliant physicist behind this conjecture, proposed that the universe has a built-in censor, a mechanism ensuring that singularities, those infinitely dense points at the heart of black holes, remain clothed behind event horizons. In other words, nature abhors a naked singularity, one that isn't hidden from the outside universe. This isn't just about modesty, it's about preserving the predictability of physics. A naked singularity would unleash chaos, bending space-time and laws of causality in ways we can't even model. Yet white holes, by their very nature, flirt with breaking this rule. If a white hole erupts into existence, spewing out matter and energy, what's to stop its core singularity from being laid bare? Unlike black holes, which trap everything behind an event horizon, white holes reverse the process, potentially leaving their singularities exposed. Imagine a cosmic magician's trick gone wrong. The rabbit isn't just pulled from the hat, the entire hat disintegrates, revealing the impossible machinery underneath. This violation isn't just theoretical drama. If naked singularities exist, they could warp reality around them, creating regions where gravity becomes unpredictable, time loops back on itself, and the laws of physics as we know them cease to apply. Some models suggest that white holes might briefly expose their singularities during eruptions before reclothing themselves, like a cosmic flash of something forbidden. Others argue that certain quantum gravity effects might prevent full exposure, acting as a microscopic censor where classical physics fails. The stakes here are enormous. If cosmic censorship fails, it wouldn't just redefine white holes, it would force us to rewrite our understanding of causality itself. Picture a scenario where a spaceship, wandering too close to a naked singularity, could emerge before it even arrived, violating cause and effect. Even Einstein's equations, which normally keep spacetime smoothly connected, might fray at the edges near these objects. Critics, of course, argue that nature wouldn't allow such a breakdown. Perhaps quantum gravity or undiscovered physics steps in to preserve cosmic modesty. After all, we've never observed a naked singularity, but then again, we've never confirmed a white hole either. The debate remains wide open, with some physicists suggesting that white holes might only expose singularities in higher dimensions or under conditions so extreme they're practically unobservable. What makes this even more fascinating is how it ties back to black holes. If a black hole's interior connects to a white hole's exterior, as some theories suggest, does the singularity stay hidden, or is it shared between them like a cosmic secret? The answer could reshape not just our view of white holes, but the very foundations of gravity, quantum mechanics, and the universe's hidden rulebook. For now, white holes stand as both guardians and challengers of cosmic order, entities that might uphold the universe's deepest laws or tear them wide open. As we push the boundaries of physics, they remind us that some of nature's most profound mysteries are still waiting, just beyond the event horizon of our understanding. Up next, we'll dive into an even more explosive possibility. What if a white hole suddenly appeared in our solar system? Now let's shift our gaze to a scenario that feels ripped straight from science fiction, but with eerie scientific plausibility. Imagine waking up one day to headlines screaming about a new cosmic neighbor, a white hole appearing without warning, erupting into our solar system. What would that look like? The moment it arrives, astronomers would spot an anomaly, a point of light flaring impossibly bright, emitting energy that defies known physics. Unlike a star, it wouldn't burn fuel. Unlike a black hole, it wouldn't pull matter in. Instead, it would vomit out radiation, particles, and perhaps even entire chunks of spacetime itself. Models suggest the outburst could dwarf the sun's luminosity in seconds, flooding our telescopes with data no one's prepared to interpret. The immediate effects would depend on where it appears. If it materialized near Pluto's orbit, we'd have time to study the spectacle from a safe distance. But if it popped up near Mars' chaos, the torrent of high-energy particles would bombard nearby planets, stripping atmospheres like a cosmic sandblaster. Earth's magnetic field might deflect some of the onslaught, but our satellites and power grids wouldn't stand a chance. Auroras would dance worldwide, not as a pretty light show, but a warning of radiation sleeting through the skies. Then there's the gravity problem. White holes aren't just radiant, they're massive. Their sudden presence would yank planets and asteroids off their ancient orbits. Picture Jupiter's path wobbling like a top losing spin, sending shockwaves through the solar system's delicate balance. Near-Earth asteroids, once predictable, could veer onto collision courses. Some models even suggest the white hole's repulsive gravity. Yes, repulsive might shove planets outward, like a ripple in a pond pushing leaves away. But the strangest twist: the white hole's lifespan. Unlike black holes, which linger for eons, theoretical white holes might be spectacularly short-lived. Quantum effects could force them to collapse within hours, even minutes. The moment it vanishes, the solar system would be left grappling with the aftermath. Reshuffled orbits, irradiated planets, and a sky now holding one less mystery, or one more, depending on what it leaves behind. The wildest speculation that it might not be entirely natural. Some physicists toy with the idea that advanced civilizations could engineer white holes as energy sources or cosmic shortcuts. If so, an explosion in our solar system might be less accident and more hello, or warning. Of course, the odds are vanishingly slim, but that's the point of white holes. They stretch imagination while testing physics. Whether as harbingers of doom or keys to new cosmic laws, their hypothetical arrival reminds us the universe doesn't play by our rules. Up next, we'll ask if white holes, like their black hole cousins, might also be bald, or if they hide even stranger features. Now let's turn to a concept that seems simple on the surface but hides cosmic complexity: the no-hair theorem, and how white holes might twist this fundamental idea. You've probably heard that black holes are considered the ultimate minimalists of the universe. According to the no-hair theorem, they can be completely described by just three features: their mass, electric charge, and spin. No other details matter, not what fell in, not how it got there, just these three numbers. But white holes, they might play by different rules. At first glance, white holes should mirror black holes in this regard. After all, mathematically, they're often seen as time-reversed versions of black holes. So if black holes are bald, white holes should be too, right? Well, not so fast. The moment we look closer, things get messy. Unlike black holes that swallow information, white holes vomit it out, and that changes everything. The no-hair theorem relies on the idea that whatever falls into a black hole is hidden forever behind its event horizon. But white holes have no event horizon to hide behind in the same way. They're all about expulsion, not concealment. Here's where it gets really interesting. Some physicists argue that white holes might actually regrow hair by spewing out the very information black holes consumed. Imagine dumping a library into a black hole. According to the no-hair theorem, that library's information is effectively gone from our universe. But if that black hole somehow became a white hole, could those books come flying back out? If so, white holes wouldn't be bald at all. They'd be cosmic storytellers, revealing secrets we thought were lost forever. Quantum mechanics throws another wrench into the works. At tiny scales, particles and forces behave in ways that classical physics can't explain. Some theories suggest that quantum effects might give white holes additional properties, extra hair, if you will, that make them far more complex than their black hole counterparts. These could include quantum memories of what fell into their predecessor black holes, or even entirely new characteristics we haven't discovered yet. Then there's the energy problem. Black holes are relatively straightforward when it comes to energy conservation. But white holes, they're theoretical energy factories, potentially creating matter and radiation out of nothing. This fundamental difference might require extra parameters to describe them properly, breaking the simplicity of the no-hair theorem. Some models even suggest white holes could have temperature-like properties or other thermodynamic features that black holes lack. The debate gets even wilder when we consider white holes' hypothetical connections to wormholes or other cosmic phenomena. If white holes really can serve as exits for wormholes, they might carry information about the other side, information that would make them anything but bald. Each of these possibilities challenges our understanding of how simple or complex cosmic objects can be. Of course, all of this remains speculative. Without an actual white hole to observe, we're left with mathematical predictions and thought experiments. But that's what makes this so fascinating. The no-hair theorem has been a cornerstone of black hole physics for decades. The mere possibility that white holes might violate it or rewrite it entirely shows how much we still have to learn about the universe's most extreme phenomena. As we continue exploring white holes' mysteries, keep in mind that every answer seems to lead to new questions. Next, we'll examine one of the most heated debates in theoretical physics, whether black holes could eventually transform into white holes over cosmic timescales. Now let's tackle one of the most mind-bending debates in modern physics, the idea that black holes and white holes might be two sides of the same cosmic coin. Could black holes over unimaginably long timescales somehow flip inside out and become white holes? This isn't just science fiction. Some of the brightest minds in theoretical physics have been wrestling with this exact question, and the answers they're uncovering could rewrite our understanding of the universe's most extreme object. The debate starts with a simple but profound question. What happens to a black hole when it's done evaporating? Thanks to Stephen Hawking's groundbreaking work, we know black holes aren't entirely black. They slowly leak energy in the form of Hawking radiation. Over trillions upon trillions of years, this process could theoretically cause a black hole to shrink and eventually vanish. But here's where things get wild. Some physicists argue that evaporation might not be the end of the story. Instead of disappearing entirely, a black hole could undergo a quantum bounce, transforming into a white hole in its final moments. Imagine this scenario: a massive star collapses, forming a black hole. For billions of years, it sits quietly in space, consuming matter and radiating energy. Then, after an almost unfathomable amount of time, it doesn't just fade away, it rebounds. The intense gravitational collapse reverses, and the black hole becomes a white hole, spewing out all the material it ever consumed. It's as if the universe hit the rewind button. This idea isn't just speculative math. It emerges from cutting-edge theories in quantum gravity, particularly loop quantum cosmology, which suggests that singularities, the infinitely dense points at the hearts of black holes, might not be the end of spacetime but rather bridges to something new. In this framework, the crushing gravity of a black hole's core could reach a limit, bounce back, and give birth to a white hole. It's a cosmic reset button turning destruction into creation. Of course, not everyone agrees. Critics argue that this quantum bounce hypothesis relies on assumptions we can't yet test. For one, the timescales involved are so vast that observing such a transition is practically impossible with current technology. There's also the question of whether the laws of physics would even allow such a dramatic reversal. The entropy of a black hole, its measure of disorder, increases as it absorbs matter. A white hole, on the other hand, would need to decrease entropy as it expels material, something that seems to defy the second law of thermodynamics. But supporters counter that quantum effects might provide a loophole. At the tiniest scales, particles behave unpredictably, and the usual rules of entropy could break down. If that's the case, then a black hole's transformation might not violate any fundamental laws. It might just operate under rules we don't yet understand. There's another layer to this debate. If black holes can become white holes, what does that mean for the information they've swallowed? One of the biggest puzzles in physics is the black hole information paradox. The idea that information entering a black hole seems lost forever, which contradicts quantum mechanics. If black holes can turn into white holes, the information might not be lost at all. Instead, it could be stored, scrambled, and eventually released like a cosmic recycling program. Yet, even if this duality is possible, the details are far from settled. Would the transition happen suddenly or gradually? Would the white hole be stable, or would it explode in a burst of energy? And most importantly, does any of this actually happen in the real universe? For now, the debate remains wide open. Some see white holes as the inevitable fate of black holes, while others dismiss them as mathematical curiosities with no physical reality. But that's the beauty of theoretical physics. It pushes us to think beyond what we can see, probing the deepest mysteries of existence. And speaking of mysteries, our next exploration takes us even further into the unknown, where scientists are attempting to recreate white holes not in space but right here in the lab. Now, let's shift our focus from the cosmic to the concrete, where scientists are bringing the mysteries of white holes down to Earth, literally. While we can't travel to a white hole or observe one in space, researchers have found a clever workaround, recreating their behavior in the lab. Using innovative materials and ingenious setups, they're simulating white hole physics right here on our planet, offering us a tantalizing glimpse into how these cosmic enigmas might operate. One of the most exciting tools in this effort is metamaterials, engineered substances with properties that don't exist in nature. By carefully designing these materials, scientists can mimic the extreme conditions around a white hole's event horizon, where matter and energy would theoretically burst outward. For example, some experiments use metamaterials to manipulate light in ways that replicate the gravitational pull of a white hole. Imagine light waves trying to escape a simulated event horizon, only to be pushed back, just as matter might be expelled from a real white hole. These lab-grown analogs don't prove white holes exist, but they help us test the math and physics behind them in a controlled environment. Another groundbreaking approach involves water waves. In a fluid dynamics lab, researchers have created white hole analogs by carefully controlling water flow in tanks. By setting up barriers and currents, they can simulate how waves behave when they encounter a white hole's theoretical boundary. In these experiments, waves approaching the simulated horizon are unable to enter, mirroring the idea that nothing can penetrate a white hole from the outside. It's a surprisingly elegant way to explore one of the universe's most exotic phenomena, using nothing more than water and precise engineering. Then there's the realm of quantum fluids, like Bose-Einstein condensates, where scientists can observe behaviors that eerily resemble white hole mechanics. These ultra-cold gases allow researchers to study how particles interact under conditions analogous to a white hole's emissions. In some experiments, disturbances in the condensate mimic the way energy might erupt from a white hole, providing clues about how information or matter could be released. These quantum systems are like tiny universes in a lab, offering a sandbox to test theories too abstract for traditional observation. But why go to all this trouble? Because white holes, if they exist, push the limits of our understanding. Lab experiments let us probe questions like, how would Hawking radiation behave near a white hole? Could information truly escape unscathed? By recreating slices of white hole physics, scientists can explore these puzzles without waiting for a cosmic white hole to reveal itself, which might never happen. Of course, these analogs have limits. A tank of water or a cloud of cold atoms can't fully replicate the space-time warping power of a real white hole. But they do provide something invaluable, testable predictions. If a lab experiment matches what theory says a white hole should do, it lends credibility to the idea. And if reality disagrees, it's back to the drawing board for physicists. Critics argue that these simulations are just that, simulations, and shouldn't be overinterpreted. Yet supporters counter that even indirect evidence is better than none. After all, many breakthroughs in physics started as thought experiments or lab models before being confirmed in the wild. The hunt for white holes, whether in space or in a petri dish, is a reminder that sometimes the universe's biggest secrets hide in the smallest details. As we wrap up this dive into lab-grown white holes, keep in mind that science often advances by bridging the gap between imagination and experimentation. And speaking of imagination, our next discovery takes us back to the stars, where white holes might hold the key to one of cosmology's most perplexing questions. Now, let's step back from the equations and experiments for a moment and consider something even more profound: the way white holes force us to rethink the very nature of reality. These cosmic mysteries aren't just about physics, they're a mirror held up to our understanding of existence itself. White holes, by their very definition, defy intuition. They're regions where matter and energy erupt into the universe seemingly from nowhere. This isn't just a challenge to our laws of physics, it's a challenge to how we perceive cause and effect. If a white hole can spew out material without any apparent input, what does that say about the unbreakable chain of events we assume governs reality? It's as if the universe is whispering that the rules we take for granted might only be part of the story. Then there's the question of existence. Black holes are cosmic vacuum cleaners pulling everything in. White holes, in theory, do the opposite. They're cosmic fountains gushing out material. But if nothing can enter a white hole, how does it know what to eject? This paradox forces us to confront whether our definitions of objects in space, things with clear boundaries and predictable behaviors, are too narrow. Maybe the universe operates on a logic that's stranger and more fluid than we've dared to imagine. White holes also stretch our concept of time. In a black hole, time slows to a crawl near the event horizon, effectively stopping from an outside observer's perspective. If white holes are their time-reversed twins, does that mean time runs backward inside them? And if so, what does backward even mean in a cosmos where time might be more like a tangled web than a straight arrow? Philosophers have long debated whether time is a fundamental property of the universe or just a human construct. White holes add fuel to that fire, suggesting our linear experience of past, present, and future might be a tiny slice of a much weirder whole. Perhaps the most unsettling implication is what white holes say about the limits of human knowledge. Science thrives on observation and evidence, but white holes, if they exist, might be forever hidden from our view. Their theoretical properties make direct detection nearly impossible, leaving us to grapple with the humbling idea that some corners of the universe might always lie beyond our reach. This isn't just a technical hurdle, it's a philosophical reckoning. How do we accept that some mysteries might remain unsolved, and what does that mean for our quest to understand everything? At the heart of all this is a deeper tension between math and reality. Einstein's equations allow for white holes, but nature doesn't seem to have signed off on them, at least not yet. This gap forces us to ask, is mathematics the ultimate guide to truth, or are there cosmic truths that math alone can't capture? It's a question that bridges physics and philosophy, reminding us that the universe is under no obligation to make sense to us. As we near the end of our journey through these 25 discoveries, the philosophical weight of white holes lingers. They're not just oddities of astrophysics, they're invitations to wonder, to question, and to embrace the unknown. And with that, we turn to our final discovery, one that looks ahead to the future of white hole research and the tantalizing possibilities it holds. Now, as we reach the final frontier of our exploration, let's turn our gaze to the future, where the next chapter of white hole research might unfold. The hunt for these cosmic enigmas isn't over. In fact, it's just beginning, armed with cutting-edge tools and bold new theories that could finally bring white holes out of the shadows of speculation and into the light of discovery. One of the most promising avenues lies in the next generation of space telescopes. Instruments like the James Webb Space Telescope, with its unprecedented infrared sensitivity, could stumble upon the unexpected, a burst of energy or a strange emission pattern that fits the profile of a white hole's theoretical outburst. Then there's the European Space Agency's upcoming Athena mission, designed to study the hot, energetic universe. While its primary focus isn't white holes, its ability to detect high-energy phenomena might accidentally catch one in the act of erupting. Sometimes the biggest discoveries come from surprises hidden in the data, but telescopes alone aren't enough. Gravitational wave detectors like LIGO and its future upgrades could play a pivotal role. If white holes are indeed the time-reversed cousins of black holes, their formation or activity might produce ripples in spacetime unlike anything we've seen. Some theorists even suggest that certain gravitational wave echoes, subtle, repeating signals following black hole mergers, could hint at white hole remnants lurking in the aftermath. It's a long shot, but in science, long shots often lead to breakthroughs. Then there's the realm of quantum gravity. Theories like loop quantum gravity and string theory are pushing the boundaries of how we understand spacetime at its smallest scales. These frameworks sometimes predict phenomena like quantum bounces, where collapsing stars rebound as white holes instead of forming singularities. If these theories are correct, future experiments probing the quantum nature of gravity, perhaps using ultra-precise atomic clocks or TABLETOP Chinese letter simulations, might uncover indirect evidence supporting white holes. The key is to think smaller, not just bigger. Computer simulations are also becoming indispensable. By modeling the extreme physics around white holes, researchers can predict what signatures they might leave behind, whether it's a peculiar gamma-ray burst, a distortion in the cosmic microwave background, or even an odd gravitational lensing effect. These virtual experiments act as a roadmap, guiding observers on where and how to look. After all, you can't find something if you don't know what it looks like. But the most exciting prospect is the open-mindedness of the scientific community itself. A decade ago, white holes were dismissed as mathematical curiosities. Today, they're taken seriously as hypothetical objects with testable consequences. This shift matters because it means more researchers are willing to chase down fringe ideas, cross-checking data for anomalies that older models can't explain. Science advances when someone asks, what if we're wrong? Of course, the ultimate question remains, what if we never find white holes? Even a null result would be profound. It would force us to ask why nature avoids these structures despite their mathematical elegance. Does the universe abhor white holes for some deeper reason we haven't grasped? Or are they hiding in plain sight, disguised as something else entirely? As we close this journey through the strange and beautiful world of white holes, one thing is clear: their mystery is a gift. Whether they're real or not, they've pushed us to question, to imagine, and to stretch the limits of what's possible, and that's the essence of discovery. The future of white hole research isn't just about answering old questions. It's about uncovering new ones we haven't even thought to ask yet. So stay curious, keep looking up, and remember, the universe always has another secret waiting. Who knows, the next time you gaze at the night sky, you might just be looking at the clue that solves the puzzle. Thanks for joining us on this cosmic adventure. Don't forget to hit subscribe and ring that notification bell so you won't miss the next journey into the unknown. Until then, keep wondering. The universe isn't done surprising us. As we wrap up this extraordinary journey through the mysteries of white holes, let's take a moment to reflect on the 25 mind-bending discoveries we've explored together. Each one has peeled back another layer of the cosmic onion, revealing just how little we truly understand about the universe. From their theoretical roots as time-reversed black holes to their potential role in the Big Bang, white holes have forced us to rethink the very fabric of reality. They've challenged the laws of thermodynamics, flirted with quantum gravity, and even offered wild possibilities like wormholes and dark matter. And yet, for all their strangeness, they've also given us something priceless, a reminder that the universe is far more imaginative than we are. Think about it, white holes defy our expectations at every turn. They spit out energy instead of swallowing it. They might hide in plain sight or exist only as mathematical ghosts. Some theories suggest they could be cosmic recycling plants, turning dying stars into newborn universes, while others argue they're nothing more than beautiful mirages in the equations of Einstein. But here's the thing, whether they're real or not, the very act of chasing these ideas has already expanded our horizons. Every dead end, every tantalizing clue, and every heated debate among scientists has pushed physics forward. What's next? The hunt isn't over. New telescopes, sharper detectors, and bolder theories are already on the horizon, each one offering a fresh chance to crack the white hole enigma. Maybe the answer lies in an unexplored corner of the cosmos, or perhaps it's buried in the quantum foam of space-time itself. One thing's for sure, the universe loves a good puzzle, and white holes are among its most tantalizing. So here's to staying curious. Whether you're a seasoned space enthusiast or just dipping your toes into the cosmic unknown, remember that every great discovery starts with a question. What if, why not, how could it be? The next breakthrough might come from a lab, a telescope, or even from someone like you, staring up at the stars and wondering what's out there. Before we go, let's not forget the cosmos is full of mysteries waiting to be unraveled. From the secrets of dark energy to the true nature of time itself, there's no shortage of wonders to explore. So hit that subscribe button and ring the notification bell, because the adventure doesn't end here. The universe has plenty more surprises up its sleeve, and we can't wait to dive into them with you. Until next time, keep looking up, keep asking questions, and never stop marveling at the wild, wonderful cosmos we call home. Thanks for joining us on this journey. Stay curious, and we'll see you in the next cosmic mystery.